Okay, last class, we left off right before we got to bond energies. We finished up with having lots of fun with expanded octets. Remember that expanded octets can occur in any compounds, any atoms that are in row 3 or lower because they have access to d orbitals. So those are like little extra pockets that they can put electrons into. And formal charges, which we also talked about last class, are one of the ways that we can tell that we need to do expanded octets. And we just nearly got to bond energies. So individual bond energies, the energy between two atoms in the bond, can be used to estimate enthalpy changes of reactions. People have gone through and done experiments where they broke very specific molecules. They saw how much energy was released when they broke those bonds. They measured it, and they figured out, here's what the bond energy is. So the bond energy is the energy required to break 1 mole of the bond in the gas phase. This number is always going to be positive. If we think of bonds as a tie between two atoms, a connecting force between two atoms, it would make sense that to break that, to disconnect those two atoms, you would have to put energy in to break that bond. Energy must be put in to break bonds. If you didn't have to put energy in to break bonds, the bonds would just randomly be breaking all the time. And we exist, so that doesn't make sense. They're not just randomly breaking, just willy-nilly. So this is always going to be positive because we have to put energy into the system being the bonds. And this is for 1 mole of that bond in the gas phase. A bond is stronger if it takes more energy to break. If our bond energy is always positive because energy is required to break the bonds, what's the opposite of breaking bonds? Forming bonds. So if the opposite of breaking bonds is forming bonds, what's the sign going to be when we form bonds? It's going to be negative, which means what? Energy is going in or coming out? Energy is going to be coming out. So if it takes energy put in to break the bonds, to snap the bonds, energy is going to come out when we form new bonds. Compounds with stronger bonds tend to be more stable and less reactive because it takes more energy to break them. Average bond energy is typically what we'll be looking at. So this is an average of the bond energies for that bond between two particular atoms among a bunch of different compounds. You can find the bond strength in like individual compounds. It's easier for us if we're just talking about generally like what is this bond strength. It's easier for us to talk about it as an average. There's little variations because of electronegativity and like, do they donate electrons? Do they pull electrons? Concepts we don't talk about in this class. There's all sorts of little forces like that that go into how strong is the bond, and so we are going to generally be talking about the average bond energy. So it can vary slightly depending on the molecule for a CH bond, just as an example. So for example, if we have methane, CH4, going to H3C plus H, so we've pulled off one of those hydrogens, our change in energy, the amount of energy we put in, is 438 kilojoules per mole. If we've got fluorines or bromines or chlorines instead of hydrogens, that bond energy changes. It's more energy if we've got a bunch of fluorines. It's a little less energy if we've got bromines. It's even less energy if we've got chlorines instead, for whatever reason. On average, our bond energy is 414 kilojoules per mole. So if we break 1 mole of these bonds, it's going to be 414 kilojoules per mole between a carbon and a hydrogen. If we had double bonds or triple bonds, this would tend to have higher energy that you need to put in to break them than single bonds. you do not need to memorize bond energies. You should know that double and triple bonds have higher bond energies. You don't need to know the actual average bond energies for any bonds, because that would be crazy. Here's a table of average bond energies. We are going to be using this for a problem in a bit. It's from the book. I'm taking a picture of it so that I have it for later, because I didn't do that earlier. The way that this table works is we've got the bonds over here on the left, and then the bond energy next to it in kilojoules per mole. We've got 3 different columns, so you would just find the thing that you're looking for. They're sort of arranged based on the thing that's on the left side. A hydrogen-hydrogen bond is going to be 436 kilojoules per mole. If we look at carbon, we've got carbon with a single bond, carbon bonded with a double bond, and carbon with a triple bond, and we can see that the bond energy increases for each of these. Delta H increases. We've also got things with carbon and nitrogen. We've got other elements over on the other side. So you just hunt for what's the specific bond that I'm looking for, and then you can copy down that value. So to estimate enthalpy changes, delta H changes, using average bond energies, it's very similar to Hess's law stuff that we were doing in previous chapters, Born-Haber cycle stuff that we were doing in previous chapters. So we can make an estimate of the enthalpy change. It's an estimate because we're using average values. We're not using the values that are specific to that particular compound. So we can estimate, remembering that bond breaking is endothermic. We have to put energy in to break bonds. And then the opposite, energy is released when we form bonds. Part of the reason on our first slide of today's lecture that I asked about, okay, what would the opposite of breaking bonds be, is because I feel like it's intuitive, or it's reasonably intuitive for us to think, okay, breaking bonds, we have to put energy in. It's not as intuitive to say that when new bonds form, energy is released. So thinking of it as opposites, I think, is helpful for getting that concept to stick. It's a little bit like changing between phases of matter. If you're going from a solid like ice to a liquid, you have to put energy in. You have to heat it up. But going from a liquid to a solid, we don't normally think of that as being an exothermic process. Energy's being released in order for it to settle down and turn into a solid. So I think this is kind of a similar situation in that way. So forming bonds is exothermic. That's where energy is released. So to find our delta H of a reaction, we can sum up. This capital sigma means sum. We can sum the delta H's of all of the bonds that are broken. That's how much energy we're putting in. So this is the total energy to break all bonds. And we can add to that the sum of all of the energy released when the bonds are formed. Total energy when new bonds are formed. And our delta H's for bonds being formed, since that's exothermic, those are all going to be negative numbers. So that's why we're adding them instead of subtracting. It'll come across as subtraction of two numbers, but that's why it's written this way. Okay, here's the slide that should look like Hess's law, Born-Haber cycle, all that good stuff. So we've got enthalpy on our y-axis. So higher up means more enthalpy, more energy. Lower down means less energy. Initially, we've got methane. We've got chlorine gas, Cl2. We put in some energy to break bonds. So one of these hydrogens gets pulled off. And we also cut these two chlorines. So now the chlorines are separated, and one of the hydrogens has been popped off. So we've broken two bonds. We broke the CH bond, we broke the Cl-Cl bond. And then, as our second step, we form a CCl bond. So the CH3 bonds with the chlorine and forms this, and the hydrogen bonds with the chlorine and forms HCl. And because energy is being released, it's becoming more stable. And if we add together these two arrows, our overall change in enthalpy of the reaction is negative. So overall, this is an exothermic reaction. So this is like a visual of what we'll be doing to solve problems with bond energies. Questions about this graph or its concepts? Cool. You may often hear the phrase, or occasionally hear the phrase, that energy is stored in chemical bonds. Breaking a chemical bond always requires energy. An energy-rich compound, or something that we might call an energy-rich compound, can undergo a reaction in which weak bonds are broken. So there's a small amount of energy in. They're weak bonds, so you don't need much energy to break them. Small amount of energy to break. And then strong bonds are formed. So unlike this graph, where there's a big jump up and a big drop down, we would be starting at a much higher level. We only increase in energy a little bit. We put a tiny little bit of energy in, and then there's a lot of energy that's released because we're forming really strong bonds, maybe double and triple bonds. So things that are explosive, TNT, for example, would fall into this category. There's weak bonds, just needs a little bit of a spark. Boom, explosion, strong bonds are formed in the process. So strong bonds are formed, lots of energy released. And again, our takeaway here, it is the forming of chemical bonds that releases energy. Forming bonds releases energy, breaking bonds takes energy. Forming bonds releases energy. Okay, here is that example. No, this is a concept question. The example is on the next slide. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? Our options are: the energy needed to break the required bonds is greater than the energy released when the new bonds form. The energy needed to break the bonds is less than the energy released when the new bonds form. Or the energy needed to break the required bonds is about the same as the energy released when the new bonds form. What does it mean for the process to be highly exothermic? It releases a lot of energy. Releases a lot of energy. Which process releases energy? Breaking bonds or forming bonds? Forming bonds. So forming bonds releases energy. If it's highly exothermic and it releases a lot of energy, and forming bonds releases energy, then forming bonds, in this case, is much greater than the amount of energy that's put in. So our correct answer here would be B. The energy needed to break the bonds is less than the energy released when the new bonds form. That's why it's highly exothermic. Question?
So, is it possible for something to be exothermic and have a positive change of energy, like absorbing energy? Because exothermic is like release of heat, right?
Release of heat, release of energy.
Is this the same?
Sort of. It's not. I'm sure it's not exactly the same, but for our purposes, yeah, it's basically the same. So no, would be the answer to your question. No, we're not going to see a case where the energy is increasing and it's also exothermic.
Is that possible?
It's probably possible. I don't think it's going to come up in this class. I think that's something that you might explore in a upper division physics class, if anywhere. Maybe not necessarily upper division, but it could show up in a physics class. We're not that worried about it. All right, a potential future fuel is methanol, CH3OH. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. I will give you some time to work on this. All right, what do we have for combustion reaction? What's our characteristics for combustion? Reacts with oxygen gas. Oxygen, the same that we breathe. Fire also needs oxygen, and combustion is, generally speaking, fire. So CH3OH plus O2 going to, what are some of our products? CO2 is one of our products, and our other product, water, H2O. So that's our basic skeletal equation for the combustion of methanol. We'll also have to balance it for our carbons. Our carbons are already balanced. We've got 1 and 1. The other element that occurs in one chemical on both sides is our hydrogens. We've got 4 in our methanol. We've got 2 in our water. To get those to balance, we need a coefficient, a number in front, of our water of 2. So 2 times 2 gives us 4 hydrogens. And then the last thing to balance is our oxygens. We currently have 3 on the reactant side, 1 in our methanol, 2 in our oxygen. And on the product side, we've got 4. We've got 2 in our CO2, and we've got 2 waters, so 2 times 1 gives us 4. The only thing that we have left that we can change without changing other things to balance this is our O2. So we can balance it with our O2. We need 1 more from our O2, and so we are going to have to put 3/2 in front of our O2. So instead of providing 2 oxygens, it's now providing 3 oxygens. This balances it out. And then we have to get rid of our fractional coefficient, and so we multiply everything by 2. So 2, 3, 2, 4. Since we multiply everything by the same number, it stays balanced, but we get rid of that fraction. So that's what we end up with for our balanced reaction. Do we want more time to work on the bond energy enthalpy calculation. I'm seeing some nodding, so we'll give you some more time for that. I would like to point out you may need to come up with Lewis structures to be able to get the correct bonds. You don't necessarily need to, but you would still need to know what types of bonds we're looking at breaking and or forming. So Lewis structures might be necessary. All right, if you need structures, this is all the bonds that you need. The lone pairs aren't important, so I'm not including them. All right, enthalpy of combustion of methanol. We need our average bond energy table. We also need the Lewis structures that we see so that we know which bonds we're pulling the values for. So let's do a count of how many of each type of bond we have. On our reactant side, these are all the bonds we're breaking. We are going to break all of these bonds. So we're using positive values for these. We have to put energy in to break all of these bonds. On the product side, we are forming all of these bonds. When we form bonds, energy is released. That's an exothermic process. We are going to calculate out how many of each of the bonds we have, and then we'll do the same thing for the product side. You could do this with have 2 of these molecules and 3 of these O2s. I'm not going to do that, partly for space concerns. Okay, in our methanol, we've got carbon bonded to hydrogen 3 times, and we've got 2 of those molecules. So we have 2 times 3 for 6 carbon-hydrogen bonds. We also have this carbon-oxygen bond, this oxygen-hydrogen bond. We've got 1 per molecule, and we've got 2 of them. So we've got 2 of each of those. The CO with a single bond, the OH also with a single bond. Some of these are going to be backwards the way that we find them in our table. And then we've got 3 oxygen-oxygen double bonds. And I'm going to shrink my methanol. So that's our full count, assuming I did everything correctly for the bonds. And we need to go to our table and find them. So we are going to find CH. This is in our table as HC, and it's got a value of 414 kilojoules per mole per bond. So that 6 times the 414 will give us a value. Our CO bond, we are going to find as C with a single bond to oxygen. It's got a value of 360 kilojoules per mole. And again, that 2 is going to multiply by that 360. For oxygen bonded to hydrogen, that's going to show in our table as HO. And it's got a value of 464 kilojoules per mole. Again, this 2 multiplying by that 464. Our oxygen-oxygen double bond is a value of 498 kilojoules per mole. And 3 times that, and we'll sum all of that. I'm doing it all in one step. to save space. So 6 times 414 plus 3 times 498 plus 2 times 360 plus 2 times 464, and I get a value of 5,626 kilojoules per mole. So that's for our energy that we're putting in to break literally all the bonds. And then on the product side, we have to count up our bonds. We've got 2 CO2 molecules. Each CO2 molecule has 2 carbon-oxygen double bonds. So coefficient of 2 times the 2 that's in each molecule. We've got a total of 4 C double bonded to oxygen bonds. If we look in our table, there's a value that's shown of 736 for C double bonded to O, but there's a little asterisk. And that asterisk below the table says that it's 799 in CO2. So we're going to use that 799 kilojoules per mole value. So it'll be 4 times 799. And then in our water, we've got hydrogen bonded to oxygen twice, and we've got 4 of them. We have 8 of those. We've got 4 for our coefficient times the 2 in each water molecule for a total of 8 HO bonds, and those have a value of 464 kilojoules per mole each. And we'll sum those up. So 4 times 799 plus 8 times 464. And this is going to be negative since we're forming these bonds. So 6908 kilojoules per mole. We add those two values together. And we get negative 1,282 kilojoules per mole overall for the reaction. Questions? I believe in the past I've made this one of the short answer questions for the relevant exam. So the places where you could go wrong, right? One of the big, I think, balancing the chemical equation, knowing what's a combustion reaction, it reacts with oxygen. If it's a hydrocarbon or carbon, hydrogen, and oxygen only, reacts with oxygen, forms CO2 and H2O. That's one place where you could screw up or not balancing it correctly. The other big area where I can foresee some problems occurring is not recognizing that oxygen O2 gas is a double bond, not recognizing that carbon dioxide has double bonds. So the Lewis structure part could also get you in trouble on this one. Okay, also related to bond energy is bond lengths. The average bond length is the average length of a bond between two atoms in a large number of compounds. Generally speaking, double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. We can say higher bond order means shorter bond. There are also stronger bonds. If we think of our bonds as rubber bands, more rubber bands, the two objects are going to be closer together because they're pulled together more closely. It'll also be harder to rip them apart because the rubber bands are stronger. So our carbon-carbon triple bond has a short bond length. It's also got the highest bond strength. Our carbon-carbon double bond is a little bit longer and a little bit weaker. Our C-C bond, single bond, has the longest of these bond lengths, and it also has the lowest bond strength. So longer bonds are generally weaker, Of course, there's exceptions. So generally speaking, stronger bonds, higher bond order, means shorter bonds. And we have a table of average bond lengths as well. I don't know that we'll use that for anything, but there they are. And there's also bonding in metals. So metals have low ionization energies because of the way that they are. We've talked about this previously. So in a metallic solid, each of our metal atoms is going to donate an electron or more to basically a sea of electrons. They just kind of, the electrons flow between the metal centers. So for example, sodium metal we can think of as an array of sodium ions with a bunch of their electrons just kind of flowing all over, around, and in between them. And these ions are held together by their attraction to the sea of electrons. So it's just kind of like the electrons are kind of like a paste or a goop that holds them together. And this does a couple of things for us. It explains the conductivity. Since the electrons are free to move, they're not stuck, they're not localized on one particular metal center. They can move freely, and so electrons can travel through wires, which is how we typically think of conductivity. It also explains their malleability, their ability to be bent, and their ability to be drawn into wires, ductility. Because they have non-directional attractions, they're a little bit more like a liquid. They can move past each other, not super easily necessarily, depends on the metal, but they can accommodate deformations because they don't have very specific single, double, triple bonds between them, like we see in crystalline structures. So the big parts here, we've got an electron sea, and the electrons are free to move. The Lewis structure of ozone is another practical application of some of the stuff that we're learning. So oxygen has a double bond, oxygen double bonded to oxygen. Ozone, I'm going to draw in one of our lone pairs, has a bent shape and it's got an intermediate bond order. So it's not locked in on a single or a double. It's got resonance structures, and so it's more like a 1.5, 1.5 bond strength. Which means that it's easier to break. And I hate the way that that looks, so let's rewrite that. 1.5. So one of the things that this means is that UV light, which can damage our skin, it's what gives us cancer. One of the things that can give us cancer and gives us sunburns, as it turns out, has just enough energy to break the bonds in ozone, but it doesn't have enough energy to break the double bond in oxygen because the double bond is stronger than the 1.5 bond order in ozone. So photons can be absorbed by ozone, and then later, just by random processes, O2 and oxygen as a radical or whatever form that it takes in the atmosphere can reform as O3. So there was this scare that's been going on for a while. It's better now, but you may have heard of the ozone hole, the hole in the ozone layer. Part of the reason that was alarming, it wasn't really happening over populated areas. It was primarily localized over the South Pole during certain seasons of the year. But that hole in the ozone layer meant that there was a lot of UV light, extra UV light that was getting through because it wasn't getting caught by this upper atmospheric ozone layer. And if that were to happen where there were people, then that would mean that we are exposed to much higher levels of UV radiation, which would be bad in terms of skin cancer reasons and also sunburn reasons. Fortunately, because of kind of worldwide protocols, the ozone layer is disappearing, and it's not really a threat anymore. So it's why you haven't heard about it probably in 10 years until now. Questions about any of that? the photon thing. So a photon, a piece of light, a packet of light, UV light. UV light has more energy than visible light. It has enough energy that the bonds in ozone are they're in the same frequency, we could think of it. So the ozone can catch the photons, and that causes some chaos in the bond and causes it to break because it has enough energy to break. It has enough energy to break in the ozone, but oxygen, being that it has a double bond, has higher energy. It's more energy required to break the bond, and so that's out of reach of the photons in the UV spectrum, at least.
So when a photon is absorbed, it forms.
It breaks the ozone. It breaks the O3.
Why does it say combines?
In a later step, the oxygen and atomic oxygen can recombine to form ozone. So the ozone is reformed at a later point. It doesn't just stay as O2. It's complex atmospheric chemistry that I'm not equipped to talk about. Okay, that'll do it for this chapter.